Namaste. I am Mrs. Arumugalakshmi.
Namaste. Today we are going to discuss the problems in Lesson 3 Magnetism and Magnetic Effects of Electric Current. First problem. A bar magnet having a magnetic moment P suffix m is cut into 4 pieces. That is, first cut in 2 pieces along the axis of the magnet, and each piece is further cut into another 2 pieces. So we are cutting the magnet along the axis, center axis we are cutting. Compute the magnetic moment of each piece. So final what piece you get, what is the magnetic moment we have to find. So what we are doing, we are cutting the magnet along the axis. So we are cutting into 4 pieces. So original length you will have it as L. It is cut into 4 pieces. So when it is cut into 4 pieces, the pole strength will be divided by 4. So the new pole strength M is equal to, that is capital M is equal to the original pole strength, that is small m divided by 4. The length will be the same. See, you are cutting the magnet along the axis. So the length will not be any change. So the length will be the same, which is equal to the original length L. Now new magnetic moment Pm is given by pole strength into length. So new pole strength is M by 4. The length is again the same, which is L. So ML divided by 4. ML is nothing but the original magnetic moment. The product of pole strength and the length is called as the magnetic moment. So M and L is the original magnetic moment of the magnet before cutting. So ML is replaced by capital M. The new magnetic moment is equal to M by 4. The next problem, a conductor of linear mass density 2 gram per meter is suspended by 2 flexible wires as shown in the figure. Suppose the tension in the supporting wires is 0 when it is kept inside a magnetic field of 1 Tesla whose direction is into the page. Compute the current inside the conductor and also the direction for the current. So here a current carrying wire is kept in a magnetic field. So it is acted upon by both electric field and magnetic field. It is given that the tension in the supporting wires is 0. That is, both the forces are balancing each other. That is, force due to the magnetic field is balanced by the downward force, which is mg. So what we are equating is mg divided by L. That is, force per length is equal to the magnetic force, which is B into L. So when you equate, you get M by L into G is equal to B into I. So our aim is to find the current inside the conductor. That is, I value you have to find. So reversing this equation for I, we get I is equal to M by L G divided by B, where M by L is the linear mass density. Linear mass density means in the given particular length of the wire, how much mass is concentrated. That is called as the linear mass density, whose value M by L value is given as 0.2 gram per meter. When you convert that into kilogram, it will be 0.2 into 10 power minus 3 kilogram per meter. Here the magnetic field B is given as 1 Tesla and G value it is 9.8. Here for our convenient we are approximating it as 10 meter per second square. So substituting all these values in the equation for current, we have I is equal to 0.2 into 10 power minus 3 into 10 divided by L. So multiplying, you get the value of I as 2 into 10 power minus 3 ampere. This is the value of current. The next problem, third one. A circular coil with a cross-sectional area of 0.1 cm square is kept in a uniform magnetic field of strength 0.2 Tesla. If the current passing through the coil is 3 ampere and the plane of the loop is perpendicular to the direction of magnetic field, calculate the total torque, total force and the average force on each electron in the coil due to the magnetic field. The free electron density for the material of the wire is given as 10 power 28 per meter cube. So here the number of turns is not given, so we will assume that the number of turn is 1. The area is given as 0.1 centimeter square, so that when we convert into meter square it will be 0.1 into 10 power minus 4 meter square. The magnetic field is given by 0.2 Tesla, current is given as 3 ampere. Here theta is equal to 0. Since the plane is perpendicular to the field, the angle between them will be equal to 0 degree. The free electron density, that is how many electrons is present, is given as 10 power 28 per meter cube. So for 1 meter cube, the electron density is 10 power 28. So first let us find the torque. You know the expression as NIBA sin theta. So substituting the value, if you substitute for theta as 0, sin 0 value is 0. So the total torque value will be 0 here. And when the torque is 0, the total force on a current loop will always be 0 in a magnetic field. So total torque we have found, total force we have found. Next we have to find the average force on each electron. So for a free electron, you know the expression for Lorentz force is F is equal to Q into V cross B. So V cross B, when you expand, it will be VB sin theta. Here the theta angle is 90 degree. So sin 90 is equal to 1. So F is equal to BQV. So from this expression we have to find, first we will find the expression for force. So before that, for V we are substituting the expression for drift velocity. Already we know the expression for drift velocity as V is equal to I divided by NQA. This equation is got from the equation I is equal to NQAV. From that equation we are finding an expression for drift velocity. Vd is equal to I by NQA. This, when you substitute in the above equation for drift velocity, we get the expression for force as F is equal to BQI by NQA. Here in the numerator and denominator we have got the same charge Q. So cancelling it, we get the expression for F as F is equal to Bi by Na, where B is the magnetic field, I is the current, N is the free electron density and A is the area. Substituting all these values as 0.2 into 3 the whole divided by 10 power 28 into 0.1 into 10 power minus 4 and simplifying, we get 0.6 divided by 0.1 into 10 power minus 28 into 10 power 4, which is nothing but 6 into 10 power minus 24. So the average force value is given as F is equal to 0.6 into 10 power minus 23 Newton. This is the proper way of representing any answer in physics. So only we rewrite the value 6 into 10 power minus 24 as 0.6 into 10 power minus 23 with the unit Newton. Fourth problem. A bar magnet is placed in a uniform magnetic field whose strength is 0.8 Tesla. If the bar magnet is oriented at an angle 30 degree with the external field, it experiences a torque of 0.2 Newton meter. Calculate the magnetic moment of the magnet. Next, work is done by the magnetic field in moving it from the most stable configuration to the most unstable configuration. And also compute the work done by the applied magnetic field in this case. So first let us find the magnetic moment. The torque is given as 0.2 Newton meter. We know the formula for torque as PB sin theta. So from this equation we are supposed to find the magnetic moment. So keep magnetic moment on one side and take the remaining terms to the other side. So we get the expression as Pm is equal to T by B sin theta. Substitute the T value, B value and theta value we get the expression as 0.2 divided by 0.8 into sine 30. Sine 30 we know that it is 1 by 2, it is 0.5. So substitute in this equation and further simplification we get 0.4 divided by 0.8 which is equal to 1 by 2 which is nothing but 0.5 ampere meter square. So the dipole moment value is 0.5 ampere meter square. Next we have to find the expression for work done. Work done is given by final potential energy minus initial potential energy. Final potential energy expression is mu b cos 180 and initial potential energy is mu b cos 0. That is, the value of u ranges from 0 to 180. So when you substitute the limits, you get these two expressions. So the total work done is equal to mu b cos 180 minus mu b cos 0. We know the value of cos pi as minus 1 and cos 0 as 1. Substituting those values, we get the work done as minus 2 mu b. Substituting the mu b value, you get minus 2 pm, that is dipole moment into magnetic field, which is B. Substituting the dipole moment which we found in the first case and magnetic field which is 0.8, substituting the value, you get the work done as minus 0.85 joules. Fifth problem. Calculate the magnetic field at the center of a square loop which carries a current of 1.5 ampere. Length of each side being is 50 centimeter. So total magnetic field produced by this loop which is in the form of a square we have to find. So first we will find what is the magnetic field produced by the single wire AB. After that it is almost the shape of a square. So the magnetic field produced by AB will be same as BC and it will be same as CD and DA also. So the total magnetic field will be 4 into magnetic field produced by AB. So first let us find the magnetic field produced by the current carrying wire AB. We know the expression for magnetic field produced by a long straight wire which is given by mu naught I by 4 pi A and it will be sine theta, integrating sine theta within the limits minus theta 1 to theta 2. This is what the expression what we had discussed in the derivation of the magnetic field produced around the long current carrying conductor. In that 5-mark question, if you see, you will get this expression. So here we have to substitute the upper limit sine theta 2 minus the lower limit is minus theta 1. Since it is in the negative y-axis, we will have minus theta 1. So you substitute it as minus of the minus limit, so it becomes plus sine theta 1. If you take theta, the theta is the angle between this AB wire and the diagonal. You know the total angle, the side angle of a square, perfect square is 90 degree. So the diagonal cuts it exactly half. So the value of theta will be 45 degree. Theta 1 and theta 2 will be 45 degree. So substituting that answer, we get mu naught I by 4 pi A. The value of A value is the distance between the point what we have chosen and the wire. So if you see the diagram itself, the total length is L and the point P is situated at a distance L by 2 from the wire. So the value of A is substituted as L by 2. Sine 45, you know the value as 1 by root 2. So 1 by root 2 plus 1 by root 2 into mu naught I 2 pi into L. That is, we cancelled this 4 pi and L by 2. The 4 in the numerator and 2 in the denominator we had cancelled. So we got this expression. So we know the answer as 1 by root 2 plus 1 by root 2 is nothing but 2 by root 2. So cancelling the 2 which is in the denominator and 2 which is in the numerator, we get the value as mu naught I root 2 pi L. So this is the magnetic field produced by the wire AB. Now we have to calculate the total magnetic field produced. So as I said, it will be 4 times the magnetic field produced by the wire AB. So it will be 4 mu naught I root 2 pi L. Now substituting the I value and L value in this expression, we get the B value as B is equal to 4 into mu naught I by root 2 pi L. 4 into mu naught value is 4 pi into 10 power minus 7. I value is 1.5. Root 2 divided by root 2 pi L value, the length value is 0.5 meter. It is given in 50 centimeter. When you convert that into meter, you will get 0.5 meter. Now cancelling the terms, pi values and simplifying, we get the answer as 3.4 into 10 power minus 6 Tesla. This is the value of magnetic field produced by a current carrying wire which is bent in the form of a square. The sixth problem. Two singly ionized isotopes of uranium-92-235 and uranium-92-238. They are the isotopes having the same atomic number but different mass number, are sent with the velocity 1 into 10 power 5 meter per second into a magnetic field of strength 0.5 Tesla normally. Compute the distance between the two isotopes after they complete a semicircle. Also compute the time taken by each isotopes to complete one semicircular path. The values given are mass of the isotopes, that is mass of 235 uranium is given as 3.90 into 10 power minus 25 kg and mass of 238 uranium isotope is given as 3.95 into 10 power minus 25 kg. Since the isotopes are singly ionized, they have equal charge which is equal to the charge of an electron. We know the value of charge of the electron as minus 1.6 into 10 power minus 19 coulomb. And we know the mass of uranium 235 and 238 are given as 3.9 into 10 power minus 25 kg and 3.95 into 10 power minus 25 kg respectively. The B value is given as 0.5 Tesla. The velocity of electron is given by 1 into 10 power 5 meter per second. First, we have to calculate the radius of the path of uranium-92-235. That is represented as R235. And we know the expression for radius as mv divided by bq. Where m is the mass of 235, v is the velocity, q is the charge value, b is the magnetic field. Substituting all these values, we get the expression as 48.8 into 10 power minus 2 meter, which is written as R235 is equal to 48.8 centimeter. This is the radius. So the diameter will be 2 into radius. So the diameter of uranium-92-235 is 97.6 centimeter. If you see the diagram, the diameter is actually the distance travelled by the uranium-235 when it is undergoing a semicircular path. Now we have found for uranium-235. Similarly, we have to find for uranium-238. After that, we have to find the distance between the two diameters. That will give you the distance between the two isotopes. So if you see the diagram, small d is the distance between the radius of 235. That is 2 into radius. 2 into radius means it is the diameter. Diameter of 235 and diameter of 238. So diameter of 238 minus diameter of 235 will give you the distance between the two isotopes after they complete a semicircle. So similarly, we have to find the radius of path of uranium-92-238, which is given as R238. We use the same formula mv divided by bq. Here the mass of 238 isotope we have to substitute. So it will be 3.95 into 10 power minus 25 into 1 into 10 power 5. The whole divided by 1.6 into 10 power minus 19 into 0.5. Further simplifying, we get the answer as 49.4 into 10 power minus 2 meter, which is nothing but 49.4 centimeter. This is the radius. So for finding the diameter, we have to multiply by 2. So the answer will be the radius of 238 into 2 is the diameter of 238 isotope, which is 98.8 centimeter. So the separation distance between the two isotopes is del D is equal to D238, that is diameter of 238 isotope minus diameter of 235 isotope, which is equal to 98.8 centimeter minus 97.6 centimeter, which is nothing but 1.2 centimeter. 1.2 centimeter is the separation distance between the isotope. Next we have to find the time taken by each isotope to complete one semicircular path. So for this we use our simple expression, that is velocity is equal to displacement by time. Displacement is nothing but the distance travelled due to the circular path, which we had already found that for 235 it is 97.6 centimeter and for 238 it is 98.8 centimeter. So substituting that in the formula, T is equal to displacement by velocity, we get 97.6 into 10 power minus 2 divided by 1 into 10 power 5, which is the velocity which is given in the question. So simplifying, you get the answer as 9.76 into 10 power minus 6 second. Similarly, the time for 238 isotope is magnitude of the displacement divided by velocity, which is nothing but 98.8 into 10 power minus 2 the whole divided by 1 into 10 power 5, which is equal to 9.88 into 10 power minus 6 second, which is 9.88 microsecond. And for 235 it is 9.76 microsecond. The seventh problem. Let E be the electric field of magnitude 6 into 10 power 6 Newton per Coulomb and B be the magnetic field magnitude 0.83 Tesla. Suppose an electron is accelerated with a potential of 200 volt. Will it show zero deflection? If not, at what potential will it show zero deflection? So an electron is said to be kept in an electric field whose magnitude is E is equal to 6 into 10 power 6 Newton per Coulomb. And again, not only electric field is there, magnetic field is also there, which is given by B is equal to 0.83 Tesla. So in a place where electric field and magnetic field are there, we are keeping an electron which is originally accelerated with the potential of 200 volt. Now we can find the value of the velocity of the electron. The velocity selector formula, you remember it as V is equal to E by B. Substituting the E value and B value, we get the value of velocity as 7.23 into 10 power 6 meter per second. When an electron goes with this velocity, it will show null deflection. Since the accelerating potential is given as 200 volt, the electron acquires, when it is accelerated, it acquires kinetic energy. Because of this accelerating potential, its kinetic energy will increase. Hence, the kinetic energy you can equate to the potential 200 volt as half mv squared is equal to E into V, where this V is the potential. From this equation, you can find the expression for the velocity, which is V squared is equal to 2EV divided by M. So, V will be equal to square root of 2EV divided by M. Now here substituting the E value, which is the charge of the electron, M value, which is the mass of the electron, and capital V as the potential, we can again find the velocity of the electron. When substituted, we get the value as square root of 2 into 1.6 into 10 power minus 19 into 200, the whole divided by 9.1 into 10 power minus 31. Simplifying this, we get the velocity as 8.39 into 10 power 6 meter per second. That is, velocity of the electron when it is accelerated by a 200 volt potential is greater than the original velocity first what we had found. So, the electron is deflected towards the direction of the Lorentz force. Lorentz force, we know that when an electron is kept in a electric field and magnetic field, it experiences a force that is called as the Lorentz force. So, in order to have the null deflection, we have to have the power supply For finding that power supply, we equate once again EV is equal to half mv square. So from this equation, V will be equal to half mv square divided by E. Now substituting the m value, mass value, E value, that is the charge value, and the velocity, which is 7.23 into 10 power 6. Substituting these values and further simplifying, we get the answer of potential as 148.65 volt. So at this potential, if the electron is accelerated, it will show zero deflection. Eighth problem. A metallic rod of linear density 0.25 kg per meter is lying horizontally on a smooth inclined plane which makes an angle of 45 degrees with the horizontal. The rod is not allowed to slide down by flowing a current through it when a magnetic field of strength 0.25 Tesla is acting on it in the vertical direction. Calculate the electric current flowing in the rod to keep it stationary. So, see the diagram which is given in the right hand side. You have a rod. That rod is placed in an inclined plane. When it is kept in an inclined plane, normally it should slide. So, for not making it slide, we are applying a current. So, a current is there around a current carrying conductor. A magnetic field is there whose value is given as 0.75 Tesla. The current value is not given and the data given is this. The rod is not sliding. That is, the magnetic field and the electric field are equated to each other. So at this point, we have to find what is the current value we are supplying. So for the forces acting on this rod, first let us draw a free body diagram. The free body diagram is shown in the left hand side. The rod is represented by the small red dot. So initially the force acting on the red dot is the gravitational force, as we know that it is the first force which is acting. So that is acting downwards. Since it is making an angle theta, the mg can be resolved into two components, mg sin theta. The value of theta is 45. So it is mg sin 45 and mg cos 45. mg cos 45 will be acting in downward direction, which that is it will be acting in the vertical direction. We are not concerned about the vertical motion. We are concerned only about the horizontal motion. So taking in account this mg sin 45 alone. This is the first force which is acting. The next force is the Lorentz force due to the presence of electric field and magnetic field. The expression for Lorentz force is F is equal to BIL. Here this BIL is inclined at an angle theta. So it can be again resolved into two components, BIL cos 45 and BIL sin 45. Since BIL sin 45 is acting vertically upwards opposite to mg cos 45, both we are not concerned. Since we are concerned about only in the movement of the rod along the horizontal direction, we neglect this. So by seeing the figure, we can draw the free body diagram expression as mg sin 45 is equal to, is balanced by, or it is balanced by BIL cos 45. So from this equation, for equilibrium of the rod, we get the expression as mg sin 45 is equal to BIL cos 45. Here we need to find the value of I. So replacing this equation for I, we get the expression as I is equal to 1 by B into M by L. M by L is nothing but the linear mass density, which is given as 0.25 kg per meter into G into sin 45 by cos 45 is nothing but tan 45. And we know the value of tan 45 as 1. So the expression becomes I is equal to 1 by B into M by L into G. So substituting the G value, M by L value, B value, you get the expression as I is equal to 9.8 ampere. So how much current we are supplying to keep the rod stationary is 9.8 ampere. The ninth problem. The coil of a moving coil galvanometer has 5 turns. So N value is 5 and each turn has an effective area of 2 into 10 power minus 2 meter square. That is, area is given as 2 into 10 power minus 2 meter square. It is suspended in magnetic field whose strength is 4 into 10 power minus 2 Weber per meter square. So this is value is B. B is equal to 4 into 10 power minus 2 Weber per meter square. If the torsional constant K value is given as 4 into 10 power minus 9 Newton meter per degree, find its current sensitivity in division per microampere. That is, current sensitivity must be in units of division per microampere. Next, we have to calculate the voltage sensitivity of the galvanometer and the resistance of the galvanometer. So, current sensitivity is given by the formula IS is equal to NAB divided by K. N is the number of turns, A is the area, B is the magnetic field, K is the constant. All values are given in the data. Substituting and cancelling, we get the answer as 10 power 6 divisions per ampere. We know that 1 microampere is equal to 10 power minus 6 ampere. Therefore, we have to write the value of current sensitivity in terms of microampere. First, we have found in terms of ampere. So, how to convert that? So, current sensitivity is given as 10 power 6 division per ampere. That is 10 power 6, which is in the numerator, bring it to the denominator. So, the value will be 1 into division divided by 10 power 6. When it goes to the denominator, it becomes 10 power minus 6. So, 10 power minus 6 into ampere. 10 power minus 6 ampere is nothing but microampere. So, the final value of current sensitivity is 1 division per microampere. Or it is 1 division microampere whole power minus 1. So, current sensitivity we have found. Next, we have to find the voltage sensitivity. So, voltage sensitivity, as we know, it is given by the formula Vs is equal to theta by V. Theta is given as 50 divisions for 25 millivolts. So, divided by 25 millivolt. Millivolt is nothing but 10 power minus 3 volt. So, the 10 power minus 3, which is in the denominator, when it goes to the numerator, it becomes 10 power 3. 50 by 25, we know the answer as 2. So, voltage sensitivity is given by 2 into 10 power 3 division per volt. So, voltage sensitivity we have found. Next, we have to find the resistance of the galvanometer, which is given by the formula Rg is equal to current sensitivity divided by voltage sensitivity. Current sensitivity, just now we have found the value as 10 power 6 division per ampere. Voltage sensitivity, we have found the 2 into 10 power 3 divisions per volt. So, dividing, we get the value as 0.5 into 10 power 3. So, 10 power 3 is kilo. So, the value is 0.5 kilo ohm. The resistance of the galvanometer is 0.5 kilo ohm. Next problem, that is the 10th problem. The resistance of a moving coil galvanometer is made twice its original value in order to increase the current sensitivity by 50%. Find the percentage change in voltage sensitivity. So that what we are doing is the resistance is doubled. So original resistance, let me have it as R suffix G. The new resistance is R dash G, which is equal to 2 times Rg. And similarly, there is increase in current sensitivity. The current sensitivity is increasing by 50%. That is, original current sensitivity is IS. The new current sensitivity is IS dash, which is given by, it is increased by 50% of IS. So, the equation is IS dash is equal to 1 plus 50% means 50 by 100 into IS. 50 by 100 is nothing but 5 by 10. 5 by 10 is nothing but 1 by 2. That is 1 plus 1 by 2. 1 plus 1 by 2 is nothing but 3 by 2. So, IS dash is equal to 3 by 2 IS, where IS is the initial current sensitivity. IS dash is the new increase in current sensitivity when the resistance is doubled as 2 Rg. So, now we have to find when current sensitivity is changing, the resistance is changing, what will happen to the voltage sensitivity? That is what the question what we have to find. So the new voltage sensitivity is given by Vs dash is equal to current sensitivity divided by the resistance of the galvanometer. So the new current sensitivity is 3 by 2 Is and the new resistance is 2 Rg. So the 2 which is that is 3 by 2, the 2 in the numerator will come to the denominator, hence it will be 3 by 4 Vs. That is, hence the voltage sensitivity decreases. Original voltage sensitivity is Vs. The new voltage sensitivity is Vs dash, which is equal to 3 by 4th of the original voltage sensitivity. Similarly, the percentage decrease in voltage sensitivity also we can find, which is Vs minus Vs dash divided by Vs into 100, which is equal to 25%.